especially Professor Xingyong Ha for giving me a chance to give a talk here. So I will talk about my recent calculations with one of my students, Dr. Huijiang Zhao. And oh, sorry. Oh. And I will talk about my talks were divided into these 5 parts. First, I want to talk about the problem. So we know that for the general hypothetical conservation laws in several space dimensions, and then Professor Jin Si and Zhou Pingxin in 1995 they proposed the following realization approximation to these systems, and then designed several numerical schemes to solve these equations. And then when the resulting, when the underlying system of conservation laws is scalar equations, for example, if for the scalar conservation laws in 2 space dimensions, here U, F, and G are scalar functions, and then the corresponding Jinxin realization scheme is this form. Here A1 and A2. This A1 and A2 are 2 positive constants. Epsilon is also a small constant. And the 2 positive constants, A1 and A2, satisfy the so-called subcharacteristic conditions. Here M is the state space, is the state space, and which will be specified later. And we will talk about this, how to choose this state space. In fact, what we are interested in is that we want to let this space to be as large as possible. And then our proposal is to study the, for example, for this. Oh, sorry. Oh, I don't know how. Page down, page up. How to say this? Oh, this? Oh, this. Oh, no. Oh, sorry. Our main proposal is to study this, the Cauchy problem of this system with given initial data. This is given initial data. We assume that the far fields of the initial data satisfy this condition. This is in one direction, they tend to some constant. So the initial data tends to some constant at one direction. For example, at the x direction. So uniformly with respect to the another direction. And here, the 2 positive 2 constants, u minus and u plus, are satisfying this kind of the left far field is less than the right far field, and science will in fact science what we are interested in is in the lifetime behavior of solutions. So we can assume the epsilon is a fixed constant in our analysis. So we can assume the epsilon equal to 1 in the rest of this talk. And the flux functions, some as flux, we will assume that the flux function f and g, these 2 flux functions are smooth enough, and it is generally nonlinear in the x direction. This means that the f is convex functions for any u belongs to the state space M. So what we are interested in is to study the so-called planar rare function wave solutions, the nonlinear stability of this kind of profile. This means this will let this R Tx is a solution, is the unique entropy solution of this Riemann problem. Since U1, the left-hand side is less than the right-hand side, and F is convex, and the its unique solutions is the rare function wave solutions is split which can be given explicitly by this. This is the solution formula for R. And to study this, since this R is, although this is continuous, but is not, its derivative has some jumps. So we must first construct the smooth approximation of the planar rarefaction wave solutions. This kind of smooth solutions was first constructed by Matsumura and Nishihara in 2000. And we will construct this one. Note that here we introduce a small constant epsilon. This is a small parameter. And then we can, this kind of property for this smooth approximation of the solutions was proved by Professor Matsumura and Nishihara. They proved that first, this means that this is it is increasing, and the LP normal, and this is the first derivative, and this is the higher order derivative of the LP estimate of the phi. This is in some sense the two facts are infected in this kind of estimates. First is, if epsilon is small, then this is small, and at t for large t, this is all small. And this means that, for example, especially for this, we can see that the LP normal for the higher order derivative of phi is also integral. From here, we can see that this is greater than 1 for I greater than 2, greater or equal than 2. And last, this phi approximates the rarefaction wave solution RTX quite well. Now we net U bar and V1 bar is the unique group solutions to the following Cauchy problem. This is, for example, this is the one-dimensional fishing of our original problems. In fact, we can show that for any given large data. In fact, this is proved by Professor Natanini in 1996 or something like that. Yeah, he proved that for this kind of Cauchy problem, if A satisfies some sub-characteristic conditions, I will mention this before below, and then this problem has a unique group solutions and satisfy that. Furthermore, we can show that this is U bar is increasing with respect to x, and this U bar tends to as time tends to infinity. This U bar tends to capital phi tx uniformly as t uniformly with respect to x as t tends to infinity. And this means that the U bar approximates the time estimated behavior of U bar is just the phi tx, the smooth approximation of the rarefaction wave solutions. And then our main proposal is that is to use the function U bar, V1 bar, and G U bar to describe the lifetime behavior of solutions. This is the U, V1, phi2 of the above mentioned Cauchy problems. So this problem is called the nonlinear stability of planar rarefaction wave solutions. So now we will reformulate this problem as follows. For example, we let the perturbation to be capital U, capital phi1, and capital phi2, and then we can use since U bar and V1 bar satisfy these equations, then we can show that the perturbation capital U, phi1, and phi2 satisfy this problem, and then the initial data becomes this one here. Then we can see that at the far fields, the initial condition tends to 0. So we can assume that the initial perturbation belongs to some Sobolev space. Then our problem is that, as I mentioned before, count the nonlinear stability of planar rarefaction wafers for the Cauchy problem. And that means we want to show that if the initial perturbation belongs to H2, and then if the Cauchy problem admits periodic solutions U, capital U, capital V1, and capital V2, such that they tend to 0 as t tends to infinity. If this holds, then we can show that the U, V1, V2 of the original of our original problem tends to R, Tx, and Fr and Gr. So this we can show the nonlinear stability of the planar rare function wave solutions. Here we note that depending on if the initial, since we assume that the initial perturbation belongs to H2, and here we have another measurement. This means the delta, means the strength of the rare function wave solutions. So if the here global stability means that if the perturbation can be arbitrarily large, then this is global. And a weak rare function wave, this means if we ask the strength of the rare function wave to be small, then we saw this is the nonlinear stability of weak rare function waves. And our main purpose is to deduce the nonlinear stability of stronger rare function waves with large initial perturbation. This is our main purpose. So about the formal results related. So first, that the results on the hyperbolic conservation laws with realization. So the Professor Taiping Liu in 1987. So he showed that for general 2x2 hyperbolic conservation laws with realization, he got the local stability of weak rare function wave solutions. For the problem, for the realization approximation to the scalar conservation laws in two space dimensions, Tao law in 1907, he got the local stability of weak planar rare function waves. So in this case, the state space M is a small perturbation of the interval u minus and u plus. Since he also asked the strength of the rare function waves to be small. So in some sense, this is state space is just a small perturbation of some point. So, and later we studied the local stability of stronger planar rare function waves. In fact, in our results, our state space is this one. Here, epsilon is for any given epsilon 0. This is any given constant, no less to be small. We will back to this later. So in this case, the state space is this one. So this space is this Bn1. This quantity was defined by Natanini in his paper. We will mention that paper later. So here, what do here epsilon? So in some sense, this seems that the solution is not a small. The state space is not a small perturbation, but to close the analysis, we need to ask the initial perturbation to satisfy some condition. So in some sense, this is still a local stability results. For other results on the nonlinear stability of planar rare function wave solutions, for dissipative conservation laws, there are some results. For example, for the scalar equations, there are some results. But for systems, I'm not so sure. Is there any results contained? So now we return to we want to state our main results. So in fact, so for example, our first result is on the case when the flux function is a general smooth and nonlinear function, and f is strictly convex. So f double, the second derivative of f is positive. In this case, we define two type of, we use two notations. The first, n10. This means that the initial perturbation, the initial perturbation is up to the first word, and n02 is that the initial perturbation is the second word, the L2 normal of the second order derivative of initial perturbation. So, the second order, yeah. So one result is that the first the perturbation is belongs to some subspace H2R, and the second assumption is on the condition on these two types of perturbation. First is that there is some constant d1 and d2. These constants are independent of the parameter epsilon. and two non-negative constants alpha greater or equal to beta, such that since let me explain this one. Since we asked epsilon to be small, so in some sense, this perturbation is small, but that perturbation, the perturbation of the second word, is can be large. But the alpha, the here two parameter alpha beta should satisfy alpha greater or equal to beta. So this is the second assumption. The third assumption is on the sub-characteristic conditions. This holds for this one. So here M1 is, in fact, this M1 is the uniform bound on the perturbation we got in our results. So if these three conditions is holds, then we can show that there is a positive constant epsilon 0, such that if epsilon belong to this this interval, then we can show that that Cauchy-Forman admits unique group solutions. This one and satisfy this, they tend to 0 uniform with respect to x and y. In fact, this implies that this holds, and this, in fact, this is the nonlinear stability of the planar rare function wave solutions. So this is our first result. Our first result is consistent with, in fact, our first result is we ask the yeah, since we as I mentioned before, since we ask epsilon to be also yeah. Oh, sorry. Since we ask epsilon to be small, as we mentioned before, so the N1 is small, N10 is small, but N02 should be large here, but the since alpha can equal to beta, so the L1 norm of initial perturbation can be large.
Epsilon is epsilon measure what? Measure how much the rarefaction wave has spread out?
In some sense, but
you have integral from somewhere to epsilon times x.
Yeah, but x can be good. In fact, I don't know. I don't understand. Just we use it to analyze, but we don't know what this means. So if x can be any given x,
right.
So I don't know what this means, but I'm not so sure.
Okay.
Yeah, okay. I think. So this is about the sub-correct condition. So this is we are modified by this the assumptions. The result, Professor Nardini's paper, this paper, and here in that paper, his analysis is based on the maximum principle. But here our results is based on the energy estimates. And then in this result, we ask the for general smooth function f and g, we ask the lower the initial perturbation to be small. And then a natural question is to how about the case when the initial perturbation, both N10 and N20 to be large. And for this case, in fact, we can show that if f and g satisfy some conditions, we can indeed get some results. For example, our second result is is that first this is the initial perturbation belongs to H2, and we ask the third derivative of f and g are uniform bounded. We ask this is uniform bounded, and then the third assumption is that we ask that there is some constant gamma less than 1/4 and a continuous increase function. We can find these functions. In fact, to prove this result, we need to construct such a hx which satisfies that as x tends to 0, this tends to infinity, such that the initial perturbation satisfies this. So in this case, we can see that since in the construction of our smooth rare function waveforms, we introduce a small parameter epsilon. So this perturbation should depend on epsilon. But here we assume that this can be large. Since D1, D4 is any given constant independent of epsilon. So this assumption means that the initial perturbation can also depend on epsilon, and as epsilon tends to 0, it also can tend to infinity. But we asked it satisfy some Gauss conditions at the epsilon tends to 0. So this kind of, and then this part is about the subcorrected condition. Here we ask F and G satisfy for enhanced subcorrected condition. This means, and K0, this is strictly less than 1. In fact, K0 is defined by this one. If A1 equal to A2, this means that this is something like 3 minus square root of 8. So since we ask if on these conditions we can show that about this problem, the same results, the results similar to that of 0, 1 can be also holders. This is our second result. This means that the initial perturbation can be large, but satisfy some Gauss condition as epsilon tends to 0. Then we can also show that this problem meets algebraic group solutions and satisfy the time-accelerated behavior mentioned in theorem 1. Oh, sorry. And our last result is consistent with the stability results for any perturbation. How about the case? In fact, in theorem 2, we asked in this perturbation can be large, but we still ask to the some assumptions on this perturbation. So how about for any perturbation? In this, for this result, we have this result. So this we ask that this is uniform bounded. The second order derivative of f and g are uniform bounded. And then this is the subcorrected conditions. And on these conditions, 3 conditions, we can show that the results holders for any perturbation belongs to H2. This is our main results. So the main ideas is that we know that the main ideas to construct group solution, the main difficulty is to control the possible groups of the solutions induced by the nonlinearity of the equations. So for the argument used before, the main idea is, for example, we assume the solution has been extended to some time step of capital T. And when we use capital NT to measure the H2 normal of the solutions, and use this to measure the strength of the rare function wafers. And then the formal result is different. In Nordhaus's argument, he used the smallness of both epsilon and delta to close the energy estimate. So his result is on the local stability of weak rare function wave solutions. And for the results we used before, the main purpose here in this result, we want to remove the smoothness on the rare function wafer, on the strength of the rare function wafers. So the first, the argument here is first to deduce this type of estimates. We can do this one based on the energy estimates and some interpolation technical. And then to use this one, his assumption n epsilon, for any given epsilon, we can obtain this kind of, based on this type of estimates, we can use this type of estimates. And here, this C epsilon 0 is a constant depending only on epsilon 0. So if we want to close the analysis, we use to ask this one and the initial perturbation to satisfy this kind of conditions. So in this argument, we do not ask epsilon to be small, but to close the analysis, we ask the perturbation to satisfy these conditions. In fact, we can see if the smooth nonlinear function satisfies some Gauss condition for large U, then for example, if the Gauss is like this one, then we can show that as epsilon tends to infinity. This constant that is tends to infinity, and in this case, we do not ask the initial perturbation to satisfy any smallest conditions. And is for this case. But our observation is the following. The main trick is to use the small parameter introduced in the construction of phi tx to control the possible growth caused by the nonlinearity of the equations. our the main observation is that if we introduce such a small parameter in phi tx, then we can show that the derivative of the u bar satisfies this kind of condition. This is have a factor epsilon to the power alpha. Here alpha is some constant, a positive constant. So if we can show this one, we can use this factor epsilon to the power alpha to control the possible growth of the solutions.
U bar is not a linear construction. Right?
U bar is the planar, the small, in some sense is the planar one-dimensional. Is the one-dimensional corresponding one-dimensional problem with the real function wave state, smooth real function state.
Oh, okay.
Yeah.
You have a Masumran, Nishihara, and then Natalini.
Yeah.
And this is one.
Yeah, this the global solution for large data for U bar is a special result of Natalini's result. For some special, choose the Cauchy data.
Yeah, right.
Yeah. But we can show that the derivative is some sense is small if epsilon is small. Yeah. And then the problem is that how to use the continuation argument to close the analysis. In other words, this means that if you can the problem is that if you can design some types of initial data, so the continuation argument can be continued. And in fact, it was in this step that we asked for example, the initial data to satisfy this type of conditions and this type of conditions. So this is the main. So last, I want to mention some key estimates mentionable. For example, if you want to deduce some estimates on U bar and Z bar, and then you use the perturbation as W and Z, and then you can perform some energy estimates to show that this is some small epsilon, and then the standard Sobolev estimates and some estimates on phi tx. This is the smooth approximation of the real function wave solution. We can deduce some. We can indeed show that the U bar, the derivative of U bar, is indeed small. And then the second type of now we deduce some type of estimates. For example, if you assume that the solution has been extended, defined on time interval 0 capital T, and the L infinite boundary norm is bounded by L, and then we can have this basic energy problem estimate. This means that the subcorrected condition holds on this interval for this state space, and if you net QL, this measures the nonlinearity of the equations and the PQ. And then if we assume that if we can choose epsilon such that this is bounded, so just one, the one is just for illustration. You can choose 2 or 1, anyway, any constant is okay. And then we can deduce this type, this is the basic energy estimate, and this is the second order energy estimate. Here, look, there was a, here you can see that there was a, this effect is also good, something for the nonlinearity. So this is the oscillation, the growth of the time step. This factor become larger and larger. So if you once we can obtain this type of estimate is natural. For example, if we can since this term n0, if we can let this then the problem is how to control this term. Then a natural idea is that we let this one to be like epsilon to the power alpha. So this epsilon control this one, and then everything is you ask this one, but even so, you cannot ask this one to be large. Since I mean the L infinite normal, here you have epsilon there. So once we ask epsilon to the alpha, and this, for example, cannot also be large. Why? So if this is large, then the L infinite normal L depends on epsilon. So we ask the bound of this one has a balance on this epsilon. Anyway, you can choose alpha, beta, and epsilon, the power of there. Then we can use the continuity argument to close the analysis. This is the first type of estimates. And the second type estimate is that for the first result is also the subdisk characteristic condition. And in this case, we'll ask this to be bounded, uniform bounded. And in this case, if this is uniform bounded, then we can obtain this kind of estimates. So from here, you can see that the Sobolev standard Sobolev estimate tells us the L infinite normal depends on the initial perturbation. So, but here we ask that the L. From here, we can give a bound on L. But here, L should satisfy this kind of estimate. So you can see here, based here, we can indeed show that if the initial perturbation, if the initial perturbation does depends on epsilon, here depends on epsilon means that as epsilon tends to 0, this tends to infinity. But we ask that the growth of this word should be must impose a growth condition on the initial perturbation so that this can be obtained. So the main idea is this one. So I think I should stop here. Thank you for your attention.
Any question, comment? I know you have been